Hello and welcome to this session on reinforcement learning, and now we're gonna go deep and see how to improve the flexibility of our approximation of the Q functions using deep neural networks. Deep neural networks are just like ordinary networks, just that they have many hidden layers and not only one. Even though in theory one hidden layer was sufficient. In practice, it's going to turn out that many hidden layers, so going deep, might be beneficial because of the high expressivity of these deep neural networks. However, there are also some drawbacks. So one question is how to make the training of these deep neural networks effective and how to avoid overfitting. Now, what we have seen so far is a shallow neural network. So we have taken a couple of Gaussian units and created a mixture of those Gaussian units. So here we have 1, 2, 3, 4, 5 Gaussian units and get a mixture of these 5 Gaussian units. They take the inputs, the features, and this is applied then to the identity function to get an output, for example. So here we have a flat mixture. Now the advantage of the deep neural networks is that we can use a hierarchical structure to get also a Gaussian mixture of a large size. But the advantage is to keep this computationally quite tractable because we use these many different layers. So what we do is we take 2 Gaussian units, for example, and sum them up. So we create a mixture here, and here we create another mixture. Then we multiply basically 2 distributions on the second hierarchical level, and then we alternate. We again sum them up, and then so on and so forth. And with this structure, which is known as the classical sum product network, we can get an exponentially large mixture of Gaussians, but the hierarchy remains linear. Now, is it an advantage to have many hidden layers? Well, there is this ImageNet large-scale visual recognition challenge that has been really a test of how much improvement you get by having more hidden layers. So here you see that the classification error of a large number of pictures that should be classified to what accordingly to what they show, that they have a classification error of 5.1% for humans, and if you use 5 hidden layers, then well, you don't really beat the humans yet. But if you include 8 hidden layers, then 19, 22, or even 152 hidden layers, then the performance is even better than that of humans. Now this is an argument why you should use deep neural networks, but deep neural networks have some challenges, and one of them is how to solve them. So we have seen that we use gradient descent to solve for the weights of the neural networks. However, there is the vanishing gradient problem. Now, what is the gradient? The vanishing gradient problem? If you have deep neural networks and as activation function the sigmoid or the hyperbolic units, then often you have the problem that your weights are gonna be very small, close to the inputs. Close to the outputs, they might be still reasonable, but the farther you go in, the lower they or the smaller they become. And that's a problem because typically the weights are initialized by random numbers, so usually between -1 and 1. And so if they're then calculated with a gradient descent or updated with gradient descent, then typically what you take as a step size is the gradient itself. And if the gradient is small, well, your learning rate, the step size, will also be very small, and so you just have random stuff because you initialized your weights randomly. And so you don't improve. And so there's a question whether this really works at all if you have too many layers. And so this vanishing gradient problem must be thought of when you use neural networks. Now, this is especially a problem if you use the sigmoid or hyperbolic activation functions because, well, you see here any input that you put into these functions is going to be between 0 and 1 here. And the gradient, the steepest gradient of this is still at 0.5, is still less than 1. For the hyperbolic, it's between -1 and 1. And also here, the derivative is always less than 1. Now, take a look at this simple example where we have an input x, and then 3 hidden layers, and then we have the output y. And so you can write this up as like this formula here at the top. And if you now initialize the weights to be -1 or 1 randomly, and we use the sigmoid function and with the derivative that is always less than 1, then if we take this and take the derivative of the output with respect to the weight 4, then we get here the sigma prime, which is this here, and that is taken times the sigmoid function, whatever we put inside A3 here. Yeah, so this is going to be between 0 and 1, and this is also going to be less than 1, so there is going to be a small number coming out of this. Now, if we go one step further, we take the derivative with respect to weight number 3, then we get here the same sigma prime of the A4. Now with the weight W4, and that's going to be something that is -1 or 1, so not doing anything to this to make it bigger, times the sigma prime A3 here, which is also between less than 1 actually. Because the derivative is always less than 1 for the sigmoid function, and we have here this thing that is similar to the sigmoid function of A3. Here it's A2 that is the argument here. And so this is gonna be in total a number that is less than 1, another number less than 1, and something between 0 and 1. And if you multiply these, and W4 could be 1, then you get something that is smaller than the first gradient. And if you continue like this, you get the vanishing gradients here. Now, there are a couple of solutions to this problem, and we will look at the rectified linear units now. So the rectified linear units, they actually have an activation function that is a piecewise linear function. So they have a 0, or the inputs that we put into this function. And so the gradient is either 0 or it's 1, and it helps for computational reasons. However, the problem is people actually didn't like the rectified linear function because it's not smooth. Yeah, so some suggested a soft version of this, so a smooth function that can approximate the rectified linear function here. However, this is actually not really helping because the soft plus function does not prevent the gradient vanishing problem because it also has a gradient that is less than 1. Now, let's summarize how deep neural networks can help modeling our complex data. We can use multiple hidden layers with the deep neural networks, and they help approximating large or continuous state and action spaces. A key challenge is, however, the vanishing gradient problem, and some solutions are the rectified linear unit activation function, and there are also others. Thanks for watching.